Hello guys, welcome to add-on. So today we are going to solve a simple numerical based on shear force diagram bending moment diagram as can be seen in the figure. So how can we solve this simple problem? So the thing is you need to first identify the different loading condition of the beam. So there are certain steps involved. So let us see what are the steps you need to follow in order to solve any problem based on shear force and bending moment diagram. So the first step is of course the drawing the FBD of the beam. The second will be to know the shear forces at every point. Shear forces at every point. We'll just see what I mean by this. So shear forces, and the third will be bending moments at every point. So the why are we drawing the FBD? So to get the reaction forces. So third, get the reaction. So these are the steps involved in order to solve the problem. So let us follow this step one by one to get to the result. So firstly, we'll see how can we make the reward diagram of the following beam. So as you can see, there is a uniformly distributed load between C and D here, and the A has a vertical force and B also have a vertical force. So there must be a roller support here. That's why the force is only in one direction. So let us draw the beam AB. So let us say this is A, this is B, and we have two vertical forces. This is FAY and this is FBY. So at C, between C and D, there is a uniformly distributed load. So it must be like here. And the distance between A and C is 2 and D and B is 4. And the total length of the beam is 10 as can be seen in the figure. So there is also a point forces at C, which is 50 kilonewton, and D also have a point force which is 40 kilonewton. So as you can see, we cannot include the entire uniformly distributed load here. We need to convert this into a point force. So how can we convert this into a point force? Because we cannot solve this solve for reactions. If we have this UDL, we need to convert this into a point force to solve the following beam. So to convert this, there are certain concepts. So the first is like whenever you have a rectangular, so the UDL also is also called as a rectangular load. So whenever you have a rectangular load, let us say the magnitude of it is let us say m kilonewton per meter, and the distance or the length of it is x. So the total magnitude will be mx. Yeah, you know that. So how it is proved that it is mx? So the thing is like let us say that the magnitude is m and we have a distance x. The total can be found out with integration. So let us integrate m dx. So this will be the total magnitude. So total magnitude of the force. So total magnitude of the force will be m dx. So whatever is the magnitude of loading into the x. So you can also match the units here, kilonewton per meter into meter, which will give us kilonewton as the force. So the in our case, in the rectangular loading case, the m is constant, which is 10. So this will be 10 integration dx from 0 to whatever the length in, let us say n, which is in our case is 4 meter between C and D. So it will be 40. So you can use this generalization everywhere. So let us say if there is a triangular node here instead of rectangular node. So the magnitude of it, let us say mx something, it will vary by with increasing x, it will vary. Mx something, it will be some function of x. So you can find a for such as integrate this some function of x dx 0 to x. If you put this function, whatever is given into here, you can find out the total force, and you can assume that the total force is acting at the center of the figure. So the center of figure in our case it will be at x by 2 because there is a rectangular figure, and in this case it will be the x by 3, and the center will be at x by 3 from this point and 2x by 3 from this point. So you can assume that it is acting on the center of the figure. So let us just rub this as you know the concept now. Now we have converted this into a point force here. Sorry. There is a beam here. So yeah, we have converted this into a point force with 40 kilonewton as the magnitude, because 10 kilonewton into 4 is 40. And the distance will be 2 from C and 2 from D, because it is situated at the center of the figure. So as you can see, now we can solve for FAY and FBY. So if we apply the equilibrium condition of beam, we can solve it. So the equilibrium conditions are summation Fx is equal to 0, summation Fy will be equal to 0, and summation of moment at any point will be equal to 0. So these three conditions you can apply in any problem based on shear force, moment, and bending moment diagram. So the thing is, like, Fx, there is no Fx in our case. There is no horizontal force, so we don't need to include this. We need to include y and moment at any point. So because if we apply the y condition, let us just apply. So Fay will be there, plus Fby will be there in the same direction, and both all of these three forces are in the downward direction, so it will be negative. For now, let us consider positive in the upward, and downward will be negative. If you can reverse this, it will not affect your solution. So it will be 50 plus 40 plus 40, which will give 130. So Fay plus Fby is 130, as we have got. Let us say this is equation 1. And you can see that there is only one equation and two variables. You cannot solve this equation unless you have a second equation. So the second equation can be get from the moment condition, which is moment at any point should be equal to 0. And for in our case, let us apply it at B, because when we will apply it at B, the force which is at B, which is the vertical force at B, will be disappear, because the couple or the moment at any point, if the force is going through that point, it will be 0, right? The moment will be 0 because of the Fby. That is why we can neglect that Fby here. That is why we will be taking at B. So let us find the moment along B. So there will be Fay into the total length, which is 10. So Fay into 10 in the clockwise direction. Again, we will take clockwise as positive and anti-clockwise as negative. Again, you can reverse this. It won't affect the solution. So Fay into 10 in the clockwise, so I have taken it as positive, will be equal to 50 into 4 plus 2 plus 2, which will be 8. So 50 into 8 plus 40 into 6, which will be because of the UDL, and 40 into 4. So as you solve this, this is 10, this is not 50. So I'll just correct this once. Fay into 10. So if you solve this, you will get something like Fay will be equal to 80 kilonewton. And you can put this into our equation 1 to get the Fby, which will be equal to, of course, the 50, because 130 minus Fy will be 50. So Fby will come out to be 50 in that case. So as you can see, we have solved for Fy and Fby now. Let us move ahead with our solution. So Fy comes out to be 80 and Fby comes out to be 50. Let's move to step 2, which was finding shear forces. So Fay is 80, Fby is 50. Both are in kilonewtons. And let's write this in a better manner. So 50. So let us calculate shear forces at every point now. If you calculate shear force at A, so just right of A. So let us calculate shear force just right of A. So just right of A, it will be Fay, right? There is a certain sign convention you need to follow here. Before this, the sign convention doesn't matter. Even if you reverse it, it will give you some same answer in the equilibrium condition. But here it does matter. So if you reverse this, the answer will be reversed. Your answer will be not the correct answer. So you need to follow this strictly. So the thing is, like, whenever you are calculating shear force on the left side of the beam, you need to take upward as positive and downward as negative. So what I mean by left side is that you have a force here. Let us say you are calculating at B. and you have force at A also, and you have force at C also. So either you can calculate from C what is the shear force at B, and or you can calculate at A from A. This will be on the left side, and this will be on the right side of B. So if you are calculating at B from the left side from A, so it will be an upward force of whatever it is, let us say FAY. So this will give you the positive at B because it is in the upward direction. So whenever you are calculating on the left, which is most of the cases we will be calculating on the left in this problem. So the upward will be considered as positive and downwards as negative. And or if you are calculating on the right side, then the reverse is true. The downward is positive and upward is negative. So that is the sign convention you need to follow. If it is not clear, it will be in the, like, when we solve the upcoming, like, when we go ahead, it will be clear. The shear force just right of 8 FAY, which will be 80 in the upper direction, which means it is positive. So it is not changing between E and C because there is no shear force between E and C. So let us calculate shear force just left of C. Just left of C, it will be same, which is 80 kilonewton in the upper direction, which is positive because there is no force in between E and C. And there is a force acting downwards at C. So if you calculate shear force just right of C, there will be two forces. One is FAY and one is 50 kilonewton acting downwards. So FAY is 80 in the upward direction and 50 in the downward. So it will give a 30 again in the positive direction. Just right of C, we have calculated this. So whenever you are like confused between, like, if there is a like sudden movement here or sudden there is a point force, so there is a trick, like you can use this as a trick. So calculate at left and right of the same point. You will get a clear idea of how is this varying at that particular point, because whenever there is a sudden force here, the shear force diagram will move suddenly from one point to another point. So it might get confusing how is it varying. So it is always suggested to calculate at left of the point and at right of the point to get a clear understanding of how it is varying at that particular point. So as you can see, there is a 40 kilometer downward force at this point, which is in the middle. And if we calculate, there is no particular point here, like there is a D and there is no particular point in between. So let us just calculate at D now, because again there is no particular point here. So shear force, let us calculate before D now, because again there is a certain force here. So we will calculate before D and after D. So before D, there is a 30 in the positive direction and there is a 40 kilonewton downward force. So it will be minus 10. There is a 30, after C there was 30 in the upper direction, and because of this minus 40 here, it goes to minus 10 kilonewton. Of course, it is in the downward direction. So let us calculate shear force after D. So what is it after D? So after D there is also a 40 kilonewton downward force acting here. And after D we are calculating, we are taking it all the forces on the left side, right now, and before this also we have calculated, let us say after C, and we have taken forces on the left. That is why we are considering upward as positive and downwards as negative, just to remember the sign convention. So after D, even if we are calculating after D, we can take all the forces here, or you can just take the FBY on the right side. Both are fine. So let us I will just explain what I mean by this. So minus 10 is here, and minus 40 is also there. So it comes out to be minus 50, right? At after D. So instead of this, considering all these forces, you could have just considered FBY in the upper direction of, then the magnitude is 50, right? And according to our sign convention, if the force is upward on the right direction, it should be negative 50. So that is right. This shear force after D is negative 50. So both the methods will give you the same minus 50 as the shear force at that particular point. So let us calculate shear force at B now. Shear force before B. So shear force before B will be same as minus 50 because there is no force between D and B. And shear force after B will be 0 because, or let us say after B there is no B. So let us just calculate at B now. at B. So at B there is a upward 50 kilonewton force and minus 50 is there and upward 50, so it will be 0 at B. Or you can call this as the right side of B, whatever you. The thing is like minus 50 will be there and the upward force will be there. So both will cancel each other and it will go to 0. That is the main concept here. So they, as you can see, we have calculated forces at all the points now. So but there is one point missing here. So I will just explain what I mean there. So there is a, as you can, you could have observed like there is a 30 kilometer upward force and there is a negative 10. So in between somewhere here, between just right of C and before D, in between here, the force goes to 0 and then it goes to negative. So we need to calculate the point where it goes to 0. So why do we need to calculate that? Because the shear force, whenever it goes to 0, the bending moment will be maximum. And we need to make the bending moment diagram also. So we need the point where shear force goes to 0. So I'll just quickly explain how to calculate that. So the bending moment is maximum at, so you can simply remember this thing that shear force, whenever the shear force is dm by dx, this is the bending moment and this is the shear force. And in some books it is also going to be minus dm by dx. So whatever your professor tells, you can follow that, if it is minus dm by dx or dx. So the main concept here is whenever if you are, let us say, function fx and you want to know that if it goes to maximum or minimum, what you do is you just differentiate and equate it to 0, right? So that you can find the x where the function goes to maximum or minimum. So if it is maximum, you take that double differential will be negative, and if it is minimum, you take that double differential will be positive. That is the basic concept of maximum and minimum from calculus. So we are using that same concept here, that whenever our shear force will be 0, which means that whenever our dm by dx will be 0, the shear force is dm by dx. So if you want the m to be maximum, the dm by dx, which is shear force, should be equal to 0. It doesn't matter if it is the double differential is negative or positive at that point, because if it is negative, then we'll just consider that it is in the downward direction, or the bending moment is in the downward direction. Or is it maximum, then we'll consider it as a positive. So what I mean is, at that point, let us say some point is there, the d by d of, which is dm by dx, will goes to 0, the shear force goes to 0. So we will calculate the moment at that point. And if it goes to positive, we'll just say that it is maximum, and if it is in the negative, we'll say that it is minimum. So we don't need to calculate the double differential and all. We can just use this basic concept here. So let us just calculate at the point where the shear force goes to 0. So the forces we have is at C, we have a upward 30 kilonewton force, as we calculated the shear force here. So 30 kilonewton will be in the upward direction, and the UDL is of 10 kilonewton per meter. Let us say somewhere x it goes to 0. So at somewhere x there is 30 kilonewton force and there is a UDL acting downwards. So somewhere at x it goes to 0, let us say, because we know that at D it is going to minus 10. So somewhere, let us say, x it is going to 0. So 30 minus 10x is 0. So the x comes out to be 3 meter here. So you can say that there is a point x such that at 3 meter the shear force goes to 0. So that is how you can simply calculate the point where the shear force is 0 and the bending moment is maximum. So now you have forces at all the point. You can just make the shear force diagram from here. Let us just check our solution once. Yeah, so you can see here that shear forces at different point. Shear force at A is plus 80. And this is shear force at C, to just left of C, because there is no forces between it. So it is plus 80. So you can check the solution if it is matching the calculation which we did. So let us just draw the shear force diagram now. This is the beam which we had. So let us say we this is A, let's say this is C, D, and B. At A, we had a shear force of, like, you can just check it here. At A, we have plus 80 kilonewton shear force, and at C, uh, just before C, we had 30. Just left of C, it is 80 still. So we can just say that it is 80, and it goes to 50 just right of C. So it will be like this. Between C and D, there is a UDL, so the variation will be inclined line. So you can see before D it is minus 10. So it is minus 10 before D, and after D it becomes minus 50. So this is minus 10, this is minus 50 after D, and the variation will be linear because there is a UDL here. And before B it is minus 50. So it is minus 50, and there is a no force between D and B, so it will be just constant. So this is how you can draw your shear force diagram according to the shear forces which we calculated earlier. Now you could have noticed that there is a linear variation between C and D because of the UDL. There was a UDL here. So whenever there is a UDL, so the shear force diagram will be inclined line, and the bending moment diagram there will be a parabola. You can just remember that the load, if the load is constant, then the shear force diagram will be inclined line, and the bending moment diagram will be a parabola. So if the load is constant, which is the case of UDL, the shear force diagram will be linear, or you can say inclined line, and the bending moment diagram will be parabolic, which is 1 degree above linear, and which is 1 degree above constant. So you can just remember that. Now let us move ahead with the BMD. So if you calculate moment at A, so we need to calculate bending moments at every point now. Let us calculate bending moment A, as you can see in the left figure. So at A, there is no, like at A and B, it will become 0 because they are in the extreme cases, and you need to consider all the forces on the right if you are calculating bending moment at A. And if you consider all the forces on the right, it will become 0 because of the equilibrium condition. So whenever you are calculating bending moment at A and B, it will become 0. So the thing is, unless you have a fixed support at any one of the supports reactions, so the bending moment at A and B will be 0, like in the extreme cases. Just when you have a fixed support, then there will be a moment also here, which is acting as a reaction. So unless you have a fixed support, you can just say that for a roller support or a hinge support, that the bending moment at A and B will be 0. So that's what I just said. So after that, you can just calculate at C. So let us say this is C. So I have calculating bending moment. Bending moment at C. So you can say that it will be force at A, which is 80. So 80 into 2 in the clockwise direction. And whenever you are taking on the left, it should, if it comes out to be clockwise, it should be positive. So it will be 80 80 into 2, which will be 160, and it is in the clockwise direction, so that's why it is positive. So the sign convention for this is, so whenever you are calculating bending moment from the forces on the left of the cross section, you need to take that clockwise as positive and anti-clockwise as negative. And whenever, like, let us say left forces you are considering, then you need to remember this. And whenever you are considering forces on the right side of the cross section, then you need to use the clockwise as negative and anti-clockwise as positive. That is the basic sign convention. Just remember the upper one. You don't need to remember the second one, because you can just reverse this. So right now we have considered forces on the left side, that 80 into 2 when we were calculating at C. So that is why we have taken clockwise as positive 160. So as we have said that at 3 meter from this, the bending moment will be maximum, or in the shear forces will be 0. As you can see, we have derived it that at x1 is 0, which is at 3 meter from the point C. You can just see, yeah, this is as s at x1 is 0. So the force will be 0 at some 3 meter from C, because what we have is we have 30 kilonewton force at C, and it will gradually decrease to 0 when it is travel at 3 meter, because there is a 10 kilometer kilonewton per meter load. Up to 3 meter will be 30 kilonewton, and it will just go to 0 at that point. So that is why we are saying that you can just calculate this, so that you have UDL, and at the start of the UDL you have 30 kilonewton force and you have 10 kilonewton per meter as the UDL value, and at some point x it is going to 0. So you can just say the 30 minus 10x is 0 and x is 3. So at 3 meter from C, the load is going to 0. So that is why we are saying that bending moment will be maximum at that point. Yeah, so let us just calculate bending moment at that point. So bending moment at x, which is 3 from C, 3 meter from C. Let us calculate that. So what we have here is a beam where there is a upward force of 80, which is at 2 plus 3, 2 meter from C and 3 meter from X. And there is also a 50 kilonewton load here. There is a 80 kilonewton load here, and there is 10 kilonewton per meter into 3, which gives to be 30 at a distance of 1.5 from X. So this is the variation of forces or the FBD of the cross section left of the cross section whenever there is a zero shear force at 3 meter from C. So this is the FBD on the left. So let us just calculate the moment here. So this is different. Yeah. So the moment will be 80 into 2 plus 3, which is 5, minus, because it the 80 into 5 was in the clockwise direction, and we are calculating on the left side of the beam. That is why that is positive, and the 50 into 3 here is in the anti-clockwise direction. That is why it is in the negative. So 50 into 3, I will just, yeah, so 50 into 3, because of this point force, is in the anti-clockwise direction. And also we have a 30 into 1.5 in the anti-clockwise direction. That comes out to be 205. Yeah, you can check this. You can just verify this. It comes out to be 205. So right now, let us calculate a bending moment at D. So either you can, let us say this is D, either you can calculate from all the forces here, or you can just consider this B force, which is a 50 into 4, which comes out to be 200 in the anti-clockwise direction, which means 200 in the positive direction, because anti-clockwise is in the right direction. So the thing is, like we have considered force on the right of the cross section. So now the anti-clockwise must be positive and the clockwise must be negative. So that is according to our sign convention. Until now we have considered on the left. You can also consider right now also on the left and calculate the force. You will get the same answer, that is in the 200 in the positive direction. The answer will not change, but it is just easy to calculate on the right now, because there is only one force and there is only one moment. And if you know the sign convention, it will be very easy to calculate on the right side now, because there is only one force. So that is why 200 into 50 into 4, 200 in the anti-clockwise, which means positive because it is on the right side of the beam. So bending moment at D is 200, and bending moment at B, we have calculated earlier also, is 0.